even though I cannot draw 30-dimensional space over here, suppose the highest, the first eigenvector over here corresponds to the highest magnitude eigenvalue, right? And suppose it is pointing in this direction. Okay, so what you will see is the 200 data points. Remember we said each image is essentially a data point, correct, in a 10,000 dimensional space. So if I take a look at the 10,000 dimensional space, even though I cannot draw it, all those 200 images will look something like this. Make it a little bit better. It will be basically, meaning if I project, if I made it this eigenvector straight. So this is the, in this direction is the highest variance between data. Sushan, can you confirm if
that's good.
That's good. Okay. So anyway, so now if this is, let's say, Bill as an example, this might be John, this might be Sally. So each one of these are now, you can see, they have more distinction in the direction of this eigenvector, right? The other thing that you will see is once we compute these eigenvectors, okay, they are perpendicular to each other, and perpendicular in math, we use the term orthogonal. Okay, so eigenvectors are orthogonal to each other. So if we take a look at the, so this was the eigenvector as an example in the direction of the, or corresponding to the highest magnitude. If we take a look at the second biggest eigenvector, it will look something like this. Third one, which is further perpendicular to maybe coming out of the board in the same way, you know, like I said, in 30 dimensions. Okay. So now what we need to do is we need to represent each of our 10,000 by 1 data point in terms of these 30 dimensions. So how do we do that? Okay, so if I go back over here. Okay, this was our I matrix, if you recall. Okay, so if you take a look at, so step 4 will be project each image. Actually, sorry, that will be step 5. Okay, compute transformed. Actually, let me make it better. Compute new basis for representing data. Okay, so if you take a look at our I matrix, right? I matrix was, if you go back over here, 10,000 by 200. Okay, if you take a look at our EV matrix, what do you see over there?
200 plus 30.
This is 200 by 30.
So it will be 10,000 by 30.
Okay, so actually let me do the other way. If I start with EV, 200 by 30. If I do EV transpose, this will be 30 times 200. You guys agree? Yes. Okay, times if I do I is
30
You have to do I transpose.
I transpose will be 200 times.
10,000.
Sorry, I was right the first time, my mistake. Otherwise, we are doing too many transpose. Let's do I transpose. No, sorry, I. I is 10,000 by 200.
EV transport.
EV, no, we don't even have to do that.
Yes,
transpose. 200, right? So, suppose I call this EF matrix. EF short for what we call eigenface. Okay. So what will be the dimension of the EF matrix?
10,000 by 30.
10,000 by 30. Everybody agrees?
Yeah.
Okay. So now how many columns will there be?
30.
30, right? How many over here?
10,000.
10,000 by 1, correct? Then second one, and total will be 30 of these, right? Now suppose we take a look at one of these, okay, convert it back to 100 by 100 and try to visualize it. Okay, same way we take a look at the second, so suppose this I call EF0, then EF1. Okay, again, so what you will see is all of these are like ghost-like images. Okay, however, this is, they give us the basis for regenerating any data. So for example, okay, so we're pretty close to putting it all together. So anyway, so now any image can be regenerated. From a linear combination of eigenfaces. Okay, for example, e.g., the I5 image, which was one of our data points, could be 0.2 times EF0 plus 0.17 times EF1 minus 0.28 EF2 plus whatever 0.1 times EF199. Sorry, EF30. We have 30 of those. 29. Okay, so how do we know what these numbers are? 0.2, 0.17, 0.28. Okay, so the very last step we do is step 5. Project each image onto the new basis. Okay, so for example, what's the size of I5? After we have converted into 10,000 by 1, correct?
Yeah.
What's the size of EF? 10,000 by 30?
Yeah.
How can I multiply this?
Transpose 1 over.
Okay, so if I multiplied it by the transpose,
No,
Sorry,
sorry.
first one. I5 transpose.
okay, if I did this transpose, then this will become
1 cross 30.
1 cross 10,000, correct? Okay, so what size will I get?
1 cross 30. Those are the values.
Those are the coefficients that if we multiply them with each one of these columns, we'll get the original image back. Okay. So to put it all together now, okay, so essentially, so now, so project all stored images. Onto the eigenfaces. So what will that happen? I0 will be represented by how many numbers? So I0 projection, meaning I0 transpose times EF, right? Wouldn't that be how many numbers?
30. 1 by 30.
Right? Same way I1 projection, I1 transpose times EF.
1 cross 30.
And same way, let's go to I199.
So 1 cross 30.
Projection equal to I199 transpose times EF. Okay, so each image has been represented by 30 numbers, right? In our database. So now how will we know which one is it? How do we recognize? So last thing, recognition procedure will be like this. Okay, suppose IX is our incoming image. Okay, so this is basically mean adjusted. So you'll convert it to grayscale, assuming it has been registered. You'll subtract the mean image from it, and suppose we call it IX. What will be the size of IX? 10,000 by 1. You guys agree? Then we'll project it onto our new bases, the eigenfaces. So then if I did IX transpose times EF, will I get 30 numbers?
Yes.
So how do we know which one is it? How do you compare 30 numbers to 30 numbers?
Index.
Correlation. The squared thing.
We can do either squared thing, right? Suppose this value is 0.8, this value is 0.7. So we can do 0.8 minus 0.7 squared plus second one. So we do it for all. Whichever produces the lowest number is most likely the match. Or we can do correlation of these 30 numbers. There's a correlation formula, right? So one of these will produce the lowest value. Whichever is the lowest value, that's the match. Okay.
Can you repeat this last part?
Okay. Were you okay up to this 30 points?
Yeah.
So now the question is, do these 30 points, are they similar to the first 30 points in our stored image or the second 30 points? So which one does it match to? If you're given a sequence of numbers, not just one number, you can do the least square difference.
Anything that tells me what matches.
Meaning this minus this square plus second number minus square, you'll get one number, right? Suppose this produced 187, the error between here and here. the error between here and here produces 203. For I8, it produces 20.8. And let's pretend this is the smallest. So what does that mean? It's similar to I8. Okay. Or we can do correlation of these. There's a correlation formula. Next time I can go over that to see which one does it correlate to better, to one of the stored images. Okay. So your next assignment over the break, you'll be programming the PCA. In the next lecture, I'll give you details how you will do it. Okay. Anyway, we'll stop here.